This question is about calcium hydroxide CaOH bracket 2. The solubility of calcium hydroxide in water can be found by titrating a saturated solution of calcium hydroxide with hydrochloric acid of known concentration. Describe how you would make a standard solution of calcium hydroxide suitable for this titration. You do not describe the subsequent titration procedure. Just how we make a standard solution, like a solution with a known concentration, a solution in which we know how many moles are there. So first what we do, we'll take calcium hydroxide, we'll add distilled water, and then we'll stir, because we want to make a saturated solution here. Saturated solution means a solution which is having a maximum amount or maximum moles at a certain temperature. So we'll take a container which is filled with distilled water, and we will add calcium hydroxide. But calcium hydroxide is partially soluble, it is not fully soluble. So we will add this calcium hydroxide into the container filled with water, and then we will stir. So when we will stir, the calcium hydroxide, some of the calcium hydroxide will dissolve, and we'll continue doing this until we see no more solid dissolve. So we'll add an excess of calcium hydroxide to water until no more solid will dissolve, and we will filter to remove the insoluble solid or undissolved solid. That will be a saturated solution. Saturated solution means a solution which contains maximum amount of solute at a particular temperature. So what we can do, we will add excess of calcium hydroxide until no more dissolve, and then we will filter to remove insoluble solid. So this will be a saturated solution of calcium hydroxide, a solution at a particular which contain a maximum amount of solute at a particular temperature. The next part, we have to do titration of this solution which we make. So what we did, we take 10 cm cube, 10.1 cm cube of portion of saturated solution is placed in a conical flask. 0.05 mole per dm cube of hydrochloric acid is added. Use the apparatus to measure exactly or accurately 10.1 cm cube. So if you want to measure 10.1, because we have a pipette 25.0 cm cube or 10 cm cube of pipette, and whenever we want to measure a single volume, single fixed volume, so we use pipette. So which apparatus is needed? We need a pipette. Suggest a suitable indicator for this titration and state the color change. So 10 cm cube portion of saturated solution we place in a conical flask. So indicator depend on what indicator you mention. Calcium hydroxide is an alkaline solution. If you mention phenolphthalein, it will be colorless. In acidic and alkaline, it is pink. So if you use phenolphthalein, it will be originally pink. But when we are adding acid from the burette, it will show a color, it will disappear. So you can mention phenolphthalein or you can mention methyl orange. If you mention methyl orange, originally it started with yellow, and the color get orange, like because the mixture is a dilute. It's not in methyl orange. When it is purely acidic solution, like fully acidic solution, then it will be red or pink. But because it's a mixture of acid and alkali or dilute solution is there, so it will turn out to be orange in color. So remember, so if we mention phenolphthalein, so originally in the conical flask we have calcium hydroxide. So when calcium hydroxide is in a conical flask, when we add drops of phenolphthalein, which is right now it is an alkaline solution. So phenolphthalein in alkaline solution or it's pink. But from the burette, we are adding hydrochloric acid. It neutralizes and it turned out to be colorless. And if you write methyl orange, then it will be yellow to orange, the color change. The next part, the following results were obtained. The initial and the final burette readings are shown. We have to fill the third titer in a table. So when to get the volume of the titer, we take a difference in the volume. So when I take the difference in the volume, it will come out as 8.95. So this will be 8.95. That is the difference in the two values. Suggests why the first titer should be discarded. Like why we should not use, this one is 8.95. So normally when we use the value, it should be zero point 0.1 more or zero point 0.1 less. That is, we include. So when we check 9.2, any value which is zero point 0.1 more, like 0 0.1 more means 9.3 and 0.1 less means 9.1. There is no value of 9.1 and 9.3, so we discard this. When we take 8.85, zero point 0.1 more means 8.95 or zero point 0.1 less 8.75, so there is 8.95, so that's why we are taking the second and the third. So why we normally, first one is a range finder, it's a rough, so normally it's a range finder and it is not concordant to zero point 0.1 or zero point 0.2 centimeter cube, that's why we discard. Some cases where rarely we take this first value if it is in the order or concordant to 0.1. So if it is concordant to, in this example it is not concordant to 0.1 centimeter cube, like it's not in the range of 0.1 or 0.1 more or 0.1 less, that's why we are not including. Or you can mention it is the first value is always a range finder or it is a rough titration, that's why most of the time we discard, we don't consider that. Calculate the mean titer. So for calculating a mean titer, we only take the one which is in the range of 0.1 more or 0.1 less, so 8.85 and 8.95. So 8.85 plus 8.95 divide, because two values are divided by 2, this will be 8.90 cm cube. Calculate the number of moles of hydrochloric acid. This is a volume of hydrochloric acid and the concentration of the hydrochloric acid, that is in the beginning they mentioned it is 0.05. So concentration multiplied by volume will give us the number of moles of hydrochloric acid. So moles equal concentration into volume, because it's a solution, 0.05 into 8.90, that is in cm cube. We have to divide by 1000 to convert into decimeter cube. This will give us the total number of moles of hydrochloric acid which are used for 4.45 into 10 to the power minus 4 moles. The equation for the reaction is given. The number of moles of calcium hydroxide in 10 cm cube portion. So we have the ratio between calcium hydroxide and hydrochloric acid, that is 1:2. According to equation, if 1 mole of calcium hydroxide, 2 moles of hydrochloric acid will react. In the last part, we work out the moles of hydrochloric acid which were used. That was 4.45 into 10 power minus 4. So if it was 4.45 into 10 power minus 4, then the calcium hydroxide will be X. So this is 4.45 into 10 power minus 4. This will be X. So we'll get the moles of calcium hydroxide, which will be half of the moles of hydrochloric acid, equal 2.25 into 10 power minus 4. So 2.25 into 10 power minus 4 are the moles of calcium hydroxide in this 10 cm cube portion. Calculate the concentration. So how to calculate the concentration? The concentration is moles divided by volume. So we have the moles and we have the volume of the solution, that is 10 cm cube. So concentration is equals to moles by volume. The moles are 2.25 into 10 power minus 4 and the volume is 10 cm cube. So we have to convert into dm cube divided by 1000. So when we divide these numbers, we'll get the concentration. So this will come out as 2.25 into 10 power minus 2 moles per decimeter cube. Then this is the concentration in moles per dm cube. The next one, we calculate the solubility of calcium hydroxide in gram per cm cube, gram per dm cube. So this is moles per dm cube. We need gram per dm cube. So these moles are present in 1 dm cube. We want how much mass is there in 1 dm cube. So we'll convert these moles into mass in gram, and we have the formula that moles equal mass in gram divided by molar mass. So mass in gram, if you want to convert moles into mass, so it will be equal to moles multiplied by molar mass. Moles we already have 2.25 into 10, because according to concentration, these many moles in 1 dm cube. So 2.25 into 10 power minus 2 moles are there in 1 dm cube. Will multiply by molar mass. For molar mass of calcium hydroxide, you will use a periodic table. Calcium is 40 plus oxygen is 16 times 2 plus hydrogen is 1 into 2. So 40 plus 32 plus 2, so it will be 74. So this will be 74. So 2.25 into 10 power minus 2 multiplied by 74. This will give us how much mass is there, mass in gram per dm cube. So this will come out as 1.65 gram per decimeter cube. So this is the solubility of calcium hydroxide. The standard enthalpy change for a reaction of calcium hydroxide and hydrochloric acid was found by reacting 0.01 mole per dm cube of calcium hydroxide with 50 cm cube of 1 mole per dm cube solution of hydrochloric acid. In a polystyrene cup, hydrochloric acid is an excess, so limiting reagent is calcium hydroxide. So we'll get enthalpy energy divided by moles of calcium hydroxide to get enthalpy change. The temperature changes from 21.2 to 26.7. Calculate the energy in joules transfer in the reaction. Use the expression energy is equals to mass into specific heat capacity into temperature change. So mass is actually, we consider that the density of the solution is 1 gram per cm cube. So what is the volume of the solution? That will be same as the mass. And when we mix hydrochloric acid 50 cm cube, as I mentioned, a solid calcium hydroxide with 50 cm cube. So that is 50 cm cube is actually the mass of the solution as well. It's a volume of solution, but as we consider the density is 1 gram per centimeter cube, so mass will be 50 as well. The specific heat 4.18 and the temperature change, the difference in the temperature. So this will be 50 specific heat is 4.18, and the temperature change 26.7 minus 21.2, so this will be 5.5. When we multiply all of them, this answer will be in joule. So this answer will be in joules, which will come out 1150 joule, 1150, and but we have to convert into kilojoule, divide by 1000, so it will be 1.1 kilojoules. So 1100 joules, which is equal to 1.1 kilojoule. And to get the enthalpy change per mole, like when 1 mole of a substance reacts, so energy which is released divided by number of the moles. In the beginning of the question, the number of the moles are given 0.01. So this energy, 11 kilojoule, this energy 1.1 kilojoule divided by the number of the moles, because enthalpy change, standard enthalpy change, is equals to energy divided by mole. Why standard? Because the condition around 25 degrees centigrade, 1 atm, solution density is 1 grams per cm cube, and we have finding for 1 mole, or 1 mole of a substance. So 1.1 kilojoule divided by 0.01 moles. So when we divide these two, this will give us, this was 1.15, okay, 1.15 divided by 0.01, so it will be 115 kilojoule per mole. But because the temperature rise in the beginning, it was 21, around changes to 26, so it means the reaction is exothermic, so we have to put a negative sign. Whenever a reaction is exothermic, there should be a negative sign for enthalpy change. The next part, we have to calculate the percentage error in the temperature. So the temperature reading which we measure, like the smallest value which we measure using this thermometer. So calculate the percentage error in the temperature change. So how temperature change is calculated? We measure initial value, we measure the final temperature, and we take a difference. So if uncertainty in one of the value is 0.1, because we are measuring it using the thermometer twice, so uncertainty will be double. So the formula for percentage error is equals to uncertainty divided by value recorded multiplied by 100. That is for percentage error, or we can also say percentage uncertainty. But because the thermometer is used twice, like when we read the first temperature, we have uncertainty of 0.1. Then we measure the second temperature, we have again uncertainty of 0.1. So what is the difference in the temperature? When we work out T2 minus T1, that will be the difference in the temperature, T2 minus T1. So the difference in the temperature, both will have uncertainty, each value have uncertainty of 0.1. So in this example, the uncertainty will be multiplied by 2. Divided by value recorded, the temperature change was 5.5 multiplied by 100. So this will give us the percentage uncertainty. So 0.2 multiplied by 100 divided by 5.5. So this is about 3.6% uncertainty. So whenever you are using the apparatus twice and then calculating a change, the uncertainty will be multiplied by 2. Like same thing happened when we are using a burette. We measure the initial volume, we measure the final volume, and then we take a difference. So uncertainty in the burette is 0.1 in each value. But because we are using it twice, so it will be double. The experiment was repeated using 50 cm cube of 1 mole per dm cube solution of nitric acid instead of hydrochloric acid. Explain why the temperature change was same for both experiments. So what is the reason why the temperature change is same for both? Because we are using the same concentration or same number of protons are used here. First we were using hydrochloric acid and now we are using nitric acid. But temperature change when hydrochloric acid reacted and nitric acid reacted is same because same number of protons are used, as the ratio between them is 1:2. The same number of protons are used for both reaction. That's why the temperature change is same for both. The experiment was repeated again using 25 cm cube of 2 mole per dm cube hydrochloric acid. Predict the temperature change of this experiment. So look, when we were using what we did now, we increases the number of the moles because 2 mole per dm cube 25 cm cube, and in the beginning it was 25. So we increases the number of the moles as, but hydrochloric acid is in excess, but as you can see the volume is reduced. In the beginning, the first experiment we were using 50 cm cube, but now we are using 25 cm cube. And what is the relation between the temperature change and the mass used? We have the formula E is equals to Cm delta T. So if same amount, or we can say E divided by C is constant, Cm is equals to delta T. So the temperature change is inversely proportional to mass of the solution used. If a smaller mass of a solution is used, the temperature change will be higher. So the first experiment, we used 50 cm cube or 50 gram of solution, the temperature change was 5.5. But the second solution is 25 cm cube or 25 gram, how much temperature change? X. But this is not proportion relation, this is inversely proportional relation. So if the mass is half, the temperature change will be double, as there is an inverse relation between the mass of solution used and the temperature. So if 25 cm cube, 50 cm cube got 5.5, 25 will cause, temperature change should be double of 5.5, that is equals to 11 degree centigrade. So the temperature change will be 11 here. Is it clear? So when we reduce the total volume of a solution for reaction and using the same number of the, because we are using the same number of the moles, but in reducing the volume, that increases the temperature change. Then justify which of this experiment 4 or 5 give the least error in the temperature. Justify your answer. Look, the percentage error or percentage uncertainty is equals to uncertainty divided by value recorded into 100. If we record a larger value, then we will have a lower uncertainty. So if I use a thermometer and measure a temperature change of 5 and I measure a temperature change of 11, because we are using a large value here and 5.5 is a small value recorded. So if value recorded is more, the percentage uncertainty will be small. So the fifth one, part 4, the temperature change was 5.5. Part 5, the temperature change is 11. So which experiment give the least error in the temperature? So experiment 5. And what is the reason for that? Because we are recording a large value. So large value, it will have a lower percentage error or it will have a lower percentage uncertainty.